Okay, so let's look at number 4. This is one of the more complex problems. And once you see it once, it's pretty helpful. So an inverted conical container, which means we have a cone standing on its point, has a diameter of 16 inches. So that means that our radius is 8 and a depth of 12. Okay, and that's the original. So what I'm going to do is I'm going to come up here and we're looking at a cone. So we want to know the volume of a right circular cone because we're talking about water flowing out. So I get pi over 3 r squared h. Okay, so volume equals pi over 3 r squared h. And it says water is flowing out. So water is dripping out. And they're always cones, just so you know, at a rate of this. Well, it's a cubic, so that's a volume. So I know that dV, and because it's going out, it's going to be negative 48. Okay. How fast is the depth of the water? So I'm going to call this height. So how fast is dH over dt when the height is 8? All right, and notice everything's in inches, so we don't need to do any converting. All right, so they really don't give you a lot of information. And you notice that our formula has 3 variables. So if I would go to do the derivative, I need to do a product rule, and I really don't have enough information to substitute back in. So the nice thing about the inverted cone, what makes it special, is as water's coming out, we have this idea of similar triangles, okay? And so no matter how high my water level is, it's a ratio of the height and the radius. So what we want to do is our goal is to eliminate at least one variable. And it depends on what information they give you, which one you want to get rid of. So since we know stuff about height and volume, that means I want to get rid of R on this problem. We could also get rid of H. It's the same idea on future problems. So similar ratios, we've got R over H. And I know that one ratio is 8 over 12. And so I want to solve for R so I can substitute it and write it in terms of H. So what we're going to do is we're going to multiply both sides by H. And so R equals reduce 2/3 H. So now I can take that and plug it in. Volume equals pi over 3 2/3 H squared times the H. And we can clean this up. So what do I get? 4 over 9 H squared. So pi times 4, 3 times 9, H squared times H. Okay, and now we just have volume and H. And we can go ahead and take our derivative, and we probably have enough information to solve that. Okay, so that's what I'm going to do. So 1 dV dt. This would be a power rule. I get what? 12. I'll simplify later. Remember, you only multiply the numerator. H squared and then times dH dt. Then we plug in what we know. So we know dV dt. I'll reduce now. So divide by 3. I get 4 pi over 9. H is now 8. And I want dH dt. So luckily, that's the only thing that's missing. Okay. So now I just do a lot of cleaning up. We get negative 48 pi. Let's see, nothing will reduce with that. So what do we get? 64 times 4. So 256 pi over 9 dH dt. And then to solve, we're going to multiply by the reciprocal. So our pi's cancel. I think 16 goes into both, but if you're not sure, let's just try something smaller. So let's divide by 4. I get negative 12, and divide by 4, I get 64. And I can divide by 4 again. So 3 times 9 over 16, and they don't have any common factors. So notice our height value, our derivative height, is negative, and that should make sense. That means that our height of the cone is decreasing. You say it the positive amount because you've already done the negative with the word decreasing. And what's our unit? Inches per minute, if you had to describe it. All right. So notice I don't say decreasing negative. That doesn't mean the same thing. All right, let's try number 5. I like number 5 because it talks about angles. So we have a kite that we are flying. I know, not drawn to scale. At an angle of elevation of pi over 3. So theta equals pi over 3, which remember is 60 degrees, but everything's always in radians. The kite string is being taken in, so I'm going to call this string, I'll call this ground, and I'll call this height. The string is being taken in like this. I see our kite's going to be coming in closer to us at a rate of 1 foot. So that means that ds is -1 because it's going to be getting smaller. If the angle of elevation does not change, and that should make sense because we can keep the same angle and still bring our kite in. How fast is the kite losing altitude? Well, altitude is height. So I want dh dt is what? Okay, so first we need to come up with a relationship that has the angle, the string, and the height. We really don't talk about the ground level at all. So I'm going to erase that because it's not relevant. Well, anytime you talk about an angle, that's a trig ratio. So I'm given the opposite side and the hypotenuse, which is sine. Sine of our angle is our height over our string. Now, because our angle never changes, I can substitute that now before you do your derivative. You actually have to. So the sine of pi over 3 is equal to h over s. I'm just going to leave that alone. Well, I need to find the sine of pi over 3. So let's do some review trig. That's 60 degrees because remember pi is 180. So our special triangles, you do have to have this memorized, is 1, √3, and 2. If I want sine, the sine of 60 is opposite over hypotenuse. So opposite over hypotenuse, which is √3 over 2. Now, at this point, height and our string are changing. So I could do the derivative, but that would be a quotient rule. And I, as a general rule, try to avoid that because it's just a lot of extra work. What we can do is we can multiply both sides by s, and we end up with √3 over 2s equals h. And now we can take our derivative. We would get √3 over 2, and then ds dt equals 1 dh dt. And then plug in what we know. Well, we know ds is -1, so negative √3 over 2, and we don't know dh. But that's what we want. And so this should make sense. Our height of the kite is getting smaller, so that's why dh was negative. Okay, so our kite is losing altitude. So losing altitude, if you had to explain this on a free response, at √3 over 2 feet per second. Okay. All right, number 6. Ooh, this one seems so innocent, but it is a lot more complicated than it looks like. Okay. All right, so what we have is we have a building. And we have a ladder. Okay, and here's ground. The ladder is 13 feet, and it's leaning against the side of the building. The foot of the ladder, which is the bottom, so I'm going to call that the ground. It's being pulled away from the building, so DG, at 8 inches per second. And this is going to be positive because it is getting bigger. How fast is the area of the triangle formed by the ladder, the building, and the ground? So we're talking about this triangle right here. Changing at the instant when the top of the ladder is 12 feet above the ground. So I'm going to call this height. So when h equals 12. Okay. So, well, if I want to know how fast an area is changing, that means I need to start with an area formula. So area equals 1/2, our base is ground, and our height is height. So 1/2 base times height. Now, as we move, as the ladder slides down, everything's going to stay this, everything's going to change except the 13. So that stays the same. But that's not part of our formula for area, ground, and height. Okay, so to do our derivative, we are going to have to do a product rule. I'm going to let that be 1 and let that be 2. dA dt is 1 times d2 plus 2 times d1. And so there's a lot that we're probably going to have to find because we really weren't given much information. Now, the other thing that you'll notice is that this is in feet and this is in inches. We can't do it the same. So I'm going to change everything to feet. So I've got 8 over 12 because I'm changing it to feet, which is really divide by 4, 2/3. Okay, so that's important. That's also what makes this problem harder. I have done this problem and forgot to convert many times, and I was mad at myself. So don't do that. So we want dA dt, which means I'm going to have to be able to find everything else. Okay, so that's an indication if you don't have it, you should be able to find it somehow. And it's not going to be easy. I told you this problem's a lot harder than it looks. So our ground level, which is G, I don't have that information at all. I have DG. So we're going to draw that final instance to try to find G. I know my height was 12 and my ladder is 13. That makes a right angle. So if you know your Pythagorean triples, this is super quick. I do. It's 3, 4, 5, 5, 12, 13. I mean, there's bunches of them. But this would be something you would have memorized years ago. Otherwise, you'd have to do g squared plus 12 squared equals 13 squared. G squared plus 144 equals 169. Subtract 144 and take the square root. Okay, so if you know your triples, you can just plug that in. And they are kind of assuming you guys know your triples, just to save time. dH dt, well, how fast is my height changing? We don't know. So that's another piece of information we need to find. So we want to find dH. So what we need to do is set up another relationship. Well, it's another triangle. I've got my ladder, I know my ground, and I know my height. So I know that g squared plus h squared equals 13 squared. I can take the derivative, plus 2h dh. And that's 169, but the derivative is 0. Then I can plug in. So I know g is now 5. I know dg is 2/3. H was 12. And I don't know dh. But now see how that's my only unknown. So what do we get? 10, 20, so 20/3. I'm going to subtract that 24 dh. So then when you divide by -24, we already have a bar here, so that -24 just goes down in the denominator. So I'll reduce, divide by 4, I get 5 and 6, so dh is equal to -5/18. Plus h, our height is 12, times 1/2, and then dg was 2/3. So now I was able to find everything, and I just have to clean it up and hope it matches what my answer says. So dA dt -25/36 plus 24/6. And then if I get a common denominator, what's that, 4, 2, 144 minus 25/36 is 119/36. Woo! Look at that. Tricky, huh? That was a lot of work. Due to the time, probably wouldn't be on an AP, but remember, I'm also just teaching you how to do related rates. All right, number 7 is actually pretty fast. So sometimes they'll give you a scenario that's unknown, and so they provide you with the formula. So we're talking about voltage, and you're not supposed to know anything about voltage, related to the current, which is I, and the resistance, which is R. And so they give you this formula. Okay? The current, which is I, is decreasing. So that means it's DI at 4. So because it's decreasing, you need to put the negative. Okay? As the resistance, which resistance is R, increases at 20 ohms. How fast is the voltage changing? Well, that's dV, not volume though. When voltage is 100 and current, which is I, is 20. Okay? All right, well, it looks like everything's changing. So there's nothing I can substitute now because nothing's staying the same. So we want to start with a product rule. So I get dV equals 1 d2 plus 2 d1. Okay. And now we can plug in what we know. Well, I want to know dV, so I should be able to find everything else. So I is 20, dr is 20. R I don't know, but di I do know. So I need to find R. So to find R, well, guess what? I never use this 100. So if I know that V equals I times R, I know that V is 100 when I is 20. And so I can use that to find R. Divide by 20, so R equals 5. Okay? And then we just clean this up. So we get 20 times 20 minus 5 times 4. So we get 380. Our voltage is changing. So I guess it's getting bigger. I don't really know anything about that. All right, so go ahead and give your problems a try. They're not going to be identical to this, so just use the process, okay? Email me if you have any questions.